We are back, section 6.3. This is all about area of oblique triangles and then applications of all the stuff that we've learned so far. So let's take a look at the area of oblique triangles. The area of oblique triangles, we did talk about this before in class when we first looked at where the law of sines comes from. We know that the area of any triangle is 1/2 times the base times the height. So that means the height of an oblique triangle, if I look right here, is going to be this hypotenuse, or B, right, if I finish labeling this, times the sine of this angle. So B times the sine of A. So that means the area is 1/2 times the base times the height, which is B times the sine of A. And that works for an obtuse oblique triangle as well. Now that means that area is 1/2 times CB times the sine of A. If C is my base, I could also think about B being my base, and then I've turned my triangle 1/2 B times A times the sine of C. Or I can think about A being my base. That means it's 1/2 times AC sine of B. I kind of just skipped through that. It all has to do with which side of the triangle you think about as your base, and then how you set up the sine ratio to solve for the height. But basically, those are our area formulas, and I believe that is on your district formula sheet, if I'm not mistaken. Yes, it is. So not anything you need to worry about memorizing, but definitely worth knowing. Okay. So let's look at example number 1. I'm going to have you try example number 2. Find the area of a triangular lot having two sides of lengths 90 meters and 52 meters and an included angle of 102 degrees. So I have an angle that's 102 degrees, and that's the included angle, so on either side I have side lengths 90 and 52. So the area is 1/2 times 90 times 52 times the sine of the included angle. Plug that into a calculator. We get 2,288.87 square meters. And that's it. So, there's really nothing else to say about that for once. I hope you understand where the formula came from, but once we know that formula, it's literally just plug and chug. So, example 2 works very much the same way. Now, there's also the case where we're not given an angle. So if I'm not given the angle of the triangle, or any angle in the triangle, how can I find the area? Happily, there is a formula from an old Greek mathematician called Heron. So Heron's formula. And that is this right here. So the area is the square root of s times s minus a times s minus b times s minus c. And s here is defined as a plus b plus c all over 2. Now, if we think about what that actually means physically, thinking about that triangle, so if I have a triangle ABC, then a plus b plus c all over 2, that's half the perimeter. So we call this the semi-perimeter. It's not something you really need to know, but you might hear me talk about the semi-perimeter, and that is something we need to solve for to be able to plug into Heron's formula. So let's take a look at example number 3. Fairly straightforward. So find the area of a triangle having side lengths 43, 52, and 72 meters. So I'm just going to right away call that A, B, and C. Okay. So I have a triangle, 43, 52, 72. Call this triangle A, B, C. Find the area. Well, I need to solve for S first. So S is A squared plus A, not A squared, A plus B plus C all over 2. So that's 43 plus 52 plus 72 all over 2. So S is 83.5. So that means the area equals the square root. It's going to be a long square root. S times S minus A times S minus B. Whoops. Times S minus C. Plug all of that into your calculator, and you will get an answer of 1,106.81 square meters. So again, it's a formula. Pretty straightforward. Plug and chug. Nothing too difficult about it, I don't think. There's a great proof of Heron's formula if you want to see where it comes from. I'm not sure we'll have time to talk about it in class, but I mean, I majored in math. I love proofs. I love explaining where these things come from. So please come talk to me. I'd love to have that conversation with you. So go ahead and try example 4 on your own. It's going to work just like example 3. And then we're going to switch gears a bit. So that was area of oblique triangles. The other half of this section is all about applications. So how can I solve word problems, real world problems for these types of triangles? So one big one that we see a lot has to do with what we call bearing. So bearing is a way of describing what direction we're going in. It measures an acute angle that a path of line of sight makes with a fixed north or south line. So what does that mean mathematically? Let's take a look. So this is how to read and draw bearings. So if I see this north 70 degrees east, I'm starting north, and then I'm rotating 70 degrees east. So this would be my bearing right here. So hopefully you do know your directions. Well, if you do, then this should be fairly simple. North 40 degrees west, I'm starting north and then I'm rotating 40 degrees to the west. So I'm going in this direction. South 15 degrees west, south, and then rotating 15 degrees west. Or south and then rotating 25 degrees east. That's basically it. So bearing, pretty straightforward. We can also talk about, or another way that we see direction written is alternate bearings. So this is where I'm given just a single degree, and I need to know what direction that's talking about. Unfortunately, as nice as it would be if this was just an angle in standard position, which we've already learned, it is not. How to read and draw alternate bearings? Basically, you're starting due north, and then you rotate clockwise, however big the angle is. So a bearing of 130 degrees, I'm starting due north, and then I'm rotating clockwise 130 degrees. A bearing of 250 degrees, I'm starting due north, and then I'm rotating 250 degrees. Bearing of 50 degrees, I'm starting due north, and then I'm rotating 50 degrees. Or bearing of 300 degrees, I'm starting due north, and then I'm rotating 300 degrees. So could I describe any of these angles using regular bearing? Absolutely. Sometimes you'll just see one used instead of the other, so you should be able to understand or be able to read each different one, and possibly convert between the two. So let's take a look at a bunch of examples. There's 4 examples here, and then we'll practice this a lot in class as well. But let's start. A ship travels 60 miles due east, then adjusts its course northward as shown. So for some reason when I printed this, when I got this document, there was no actual picture of this. So pretend that this is the picture as shown. So this is point A, it's where we're starting. The ship goes 60 miles due east to point B, and then it adjusts its course northward. So it starts going further north, not directly north, but further north, to angle C. And then after traveling 80 miles, so once it gets to point C, The ship is 139 miles from its point of departure. So that means from A to C is 139 miles. Describe the bearing from point B to point C. Okay, it's an excellent question. So let's take a look. So finish labeling our triangle. This is an oblique triangle. If I need to know the bearing from B to C, then I'll need this angle in here. Angle B. I know 3 sides. So to find an angle, side, 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 that means I need the law of cosines. So I'm going to use the alternate form since I'm solving for an angle measure. Cosine of B equals 80 squared plus 60 squared minus 139 squared all over 2 times 80 times 60. Take the inverse cosine of both sides and I'll get B is about 166.15 degrees. So that's this whole angle in here. However, I need the bearing. So bearing measured, well, I'm going north, so I'm going to have a bearing starting north. And then, however far, in this case, east. So I really only need this part of the angle. Now, a lot of these word problems are going to depend on you being able to set up the picture and think about angles and right angles and 180 degrees and so on from geometry. So going due north, that means this was a right angle. So all of angle B is that angle that I actually need plus 90 degrees. Right? Because I need to know the angle from straight north to point C. And so if I'm solving for that angle, that means I have 166.15 degrees. Subtract that right angle out to get what I have left. So my bearing is north 76.15 degrees east. Now, that was kind of a lot. We're going to go through that in class too. But please pause this, rewatch this, come to me if you have questions. Let's look at example 6. Example 6 is really interesting, actually. Of course, I would think that, but hopefully you agree. The course for a boat race starts at point A and proceeds in the direction south 52 degrees west to point B. So let's chunk this. Take it one piece at a time. I'm starting at point A, and then I go south 52 degrees west. So along there. And I'm following that until I get to point B. And then from point B, then in the direction south 40 degrees east. So south 40 degrees east to point C. And point C, and then finally back to point A. It says point C lies 8 kilometers directly south of point A. Approximate the total distance of the race course. So in other words, I need the perimeter of this triangle. I need to add up the side lengths A, B, and C. So, how can I do that? Well, I have this one angle here, luckily, 52 degrees. I need 2 other angles, B and C. This is what I mean when I say that you'll need to remember your angle rules from geometry. So if I look here, I have 2 parallel lines. I'm going to use a different color here, make it a little more clear. I have 2 parallel lines right here, and then this angle intersecting them. So this angle, 40 degrees, is going to be the same as this interior angle. So angle C is 40 degrees. Angle C is 40 degrees. Angle A is 52 degrees. That means angle B is going to be 180 minus A plus C, or 180 minus 92 degrees, 88 degrees. So now that I know the angles, I can figure out the other two side lengths. I know one side length, so I'm going to go ahead and just use the law of sines because it's a little simpler. So B over the sine of angle B equals A over the sine of angle A. So A equals 8 times the sine of 52 degrees all over the sine of 88 degrees. Plug that into a calculator, round to 2 decimals, that's 6.31 kilometers. To solve for C, I have B over the sine of B equals C over the sine of angle C. So C equals 8 times the sine of 40 degrees all over the sine of 88 degrees, which rounds to 5.15 kilometers. So my total distance is 6.31 kilometers plus 5.15 kilometers plus 8 kilometers for a grand total of about 19.46 kilometers for the race. So I do think that was interesting. Just from like 2 angles, I was able to figure out the distance of this race course. It's fascinating to me. But I'm sure you disagree. Hopefully I'm starting to change some of your minds. Let's look at example 7. Due to winds, a tree grew so it was leaning 4 degrees from vertical. At a point 35 meters from the tree, the angle of elevation to the top of the tree is 23 degrees. What is the height of the tree? So how generous they gave us a picture. So I see right away that I have angle, side, angle. Angle, side, angle. So what is that? Law of sines. So let's use the law of sines to solve. I'm going to need this last angle up here, so that's going to be 180 minus 23 plus 94, or 63 degrees. So I have 35 meters over the sine of 63 degrees equals the height over the sine of the angle opposite that, over the sine of 23 degrees. H equals 35 times the sine of 23 degrees, all over the sine of 63 degrees. That approximates to 15.35 meters. Pretty straightforward, I think. Just recognizing the given information and then using the law of sines to solve. All right, one more problem. And then we're done with this section. All right, we're under 20 minutes. I'm going to try to keep this brief. So example number 8. A plane flies 400 kilometers at a bearing of 310 degrees from Dallas to Amarillo, Texas. The plane then flies 710 kilometers to Roswell, New Mexico, due west of Dallas. Find the bearing of the flight from Amarillo to Roswell. Let's set up a picture. So a plane flies 400 kilometers at a bearing of 310 degrees from Dallas to Amarillo. So we're going to start in Dallas. And then it flies 400 kilometers at a bearing of 310 degrees from Dallas to Amarillo. So let's find what that bearing is. 310 degree bearing, that means I'm starting due north, and then I'm rotating clockwise 310 degrees. So I'm going in this direction. And I fly in that direction for 400 kilometers until I get to Amarillo. The plane then flies 710 kilometers to Roswell, due west of Dallas. So due west of Dallas puts Roswell over here. And I'm flying 710 kilometers from Amarillo to Roswell. So this is 710 miles. All right. Find the bearing from Amarillo to Roswell. Let's take a look. Let's see. I have 2 sides and I need some angles here. Luckily, we have a way to figure those out. So let's start. I know that I was starting due north and then I rotated 310 degrees. This was due west of Dallas. So if I see here rotating here, I'm going to use another color again. I rotated 270 degrees and then the rest of the way to get to 310. In other words, this angle in here is 310 minus 270, or 40 degrees. So that's a 40-degree angle. Let's see, what else can I solve for? Now that I know this angle in here, can I solve for this angle? 710 over the sine of 40 degrees equals 400 over the sine of, we'll just call this theta. So the sine of theta is 400 times the sine of 40 degrees, all over 710. Inverse sine of both sides, so that angle in there is about 21.23 degrees. Great. What else do I need to finish solving this? Well, again, geometry. Those are parallel lines, and then this line is intersecting. This angle measure is equal to this angle measure, so in here is 21.23 degrees. And if I want bearing from Amarillo to Roswell, then I need this angle. It's kind of hard to see. This angle right here. Well, starting north, I know that's 180 plus whatever this is. Hopefully you see that. So I need this angle in there. I know this is a right angle. So 90. And then part of it is 21.23, so the rest of it is going to be subtract that. So 21.2, or 90 minus 21.23, it's going to give me what, 68.77. So the angle, the bearing, is going to be 180 plus 68.77 degrees. 248.77 degrees from Amarillo to Roswell. Okay, that was kind of a lot, and it was a little hard to explain over a video. So hopefully some of you caught on. If not, we'll definitely go through that example in class, and we'll spend quite a bit of time on it. But for now, that's about it. These are the kinds of questions you'll see. A lot of bearing questions, a lot of questions using oblique triangles. Practice, come to class with questions, and have a great day. Thank you so much.